Hello everyone. In this video we are going to discuss about kinematics. In this course we are going to talk about the kinematics of particles and rigid bodies. For particles we are going to be concerned mostly with their translation only. And given the trajectory as shown here, we will calculate their translation only. Whereas for rigid bodies we are going to be concerned both with the translation and rotation. Now let's take the example of a particle. We want means to describe the motion of this particle. The question is, where should we start? What should we do to be able to describe the motion of the particle? The answer relies on the coordinate system. So every time we are going to discuss motions of particles or rigid bodies, we'll start defining our coordinate system. And during this course, we are going to discuss three types of coordinate systems: rectangular, polar, and the normal tangential or NT coordinate system. Within the context of kinematics, we will learn how to describe position, displacement, velocity, and acceleration. By position, we mean, leaving this example of an aircraft flying over this trajectory shown by the dashed lines. Here we are using, by the way, the rectangular coordinate system that we are going to cover in the next video. When I represent this body, which is an airplane, as a particle, I'm going to take its coordinates at its center of gravity, as shown here. And its coordinate, using this rectangular coordinate system, is given by the position vector r, as shown here. Now, if we take the position at two different instants of time, t1 and t2, we can then calculate the displacement of the aircraft. Again, we are representing the aircraft as a particle. So at instant t1 we have position vector r1, shown here, and at the instant of time t2 we have the position vector r2 shown here. The displacement for this given instance of time is called here delta r. Now, calling the difference of instants delta t, so t2 minus t1, we can then calculate our average velocity, as shown here, which is by definition delta r divided by delta t. The instant velocity, on the other hand, is defined as the limit of the average velocity when delta t goes to 0. In fact, this gives us a differential equation which is equal to dr dt. Next, we can move on to the calculation of speed. So speed is a scalar value, don't forget that. It's a scalar value, whereas the velocity is a vector. So when we use the rectangular coordinate systems in 2 dimensions, as we are going to extensively cover during this course, we can represent a general velocity vector as shown here, with a component along the x direction and another component along the y direction. And the magnitude of this vector is defined as the speed. Again, this will be a instantaneous speed because it was based on a instantaneous velocity vector, and this will be a average speed. Finally, considering again our airplane in two different instants of time, we have to be able to define its velocity vector at the 2 instants of time in order to calculate its acceleration. Note here a very important observation, that velocity vector is always tangent to our path. So our path is defined by this dashed line here, and at instant of time 1 or t1, our first velocity vector is tangentially represented here, And the second velocity vector at instant t2 is also tangential to the trajectory here. Don't forget that. So again, given that delta t represents t2 minus t1, the average velocity can be calculated between the difference between the two velocity vectors divided by delta t and the instantaneous acceleration, the instantaneous acceleration can be calculated as the limit of the average acceleration when delta t approaches 0. In fact, that gives us with a second differential equation used in kinematics that relates acceleration with velocity. I hope you liked this video, and I'm looking forward to see you in the next video.